All right. Hey, I apologize for being a little tardy today. I talked to another teacher about something we have going on. For today, flip to that slide, beginning on Wednesday, because today is not Wednesday, it's Thursday. Sorry. What we're going to talk about today is essentially called moment of inertia, and is the ability for an object that rotates, for us to figure out why it's hard to rotate the object, or why it requires more torque, or why it requires less torque to move an object. Okay? That's what we're going to do today. The first slide just essentially tells you how to calculate moment of inertia. You have torque and angular acceleration. It also relates it to F equals ma, Newton's second law. The reason why it does that is because if you think about what torque is just force times the lever arm, and that's it. Okay? So we can relate this quite easily. What is alpha in this case? What is that right term? What is alpha? Not the beginning. It's a Greek letter. What does it mean?
It's acceleration.
Angular acceleration. You're correct. Okay? It's on the right next to the I. It is like this. That is the alpha symbol. Yes, that is your angular acceleration. Okay? So, let's think about what moment of inertia is for a second. F equals ma, tau equals I alpha. So, I and mass are quite similar. So, moment of inertia and mass are very similar. Okay? If you think about what inertia is, inertia depends on what? Mass. That's the only thing that inertia depends on. So by us saying it's the moment of inertia, we are still relating that to, it's really dependent on mass. Okay? Specifically, moment of inertia deals with where that mass is located and how much there is. So if you read it, it says I depends on both the mass, so how much mass you have, and then where it's located in that circle or in that sphere, in whatever object you have. So is it located at a fixed point? Is it located on the outside perimeter of that object? That's what I depends on. Okay? There's one formula to calculate moment of inertia, but we will manipulate that for different objects, as we'll see. If the mass is distributed farther from the axis of rotation, moment of inertia will be larger. Okay? What that means is if I have this meter stick and I tape a hook to the meter stick, okay? For us to rotate this, it's easier to rotate it when all that mass is centered closer to the axis point than if it's further away, okay? This will be a lot harder to move, okay? It'll be a higher moment of inertia. Here's the formula that we're going to use to calculate moment of inertia. This right here is wrong. I equals IR squared. Why, you might say? That's like me saying, yeah, I mean, it's completely illogical. I'm trying to think of any scenario where that would even be close to true. But it's like me saying an apple equals an apple plus 2 oranges. That's not true. Okay? Because I is I. It's not, you can't really substitute I there. It makes sense in my head. Either way, that formula is not right. Here's the formula we're going to use. If I explain right. Is I equals mr squared. So it was really close.
So mass?
Yes! Mass. It's also your vector. Okay? What does R stand for?
Duration.
Radius, yes. Okay. It is absolutely radius of the circle. Which in that case, you see it? This is going to be true for a hollow cylinder. Okay, I will give you several formulas for these different objects. But see how this is a hollow cylinder? There's nothing inside, and then you have just whatever's on the outside. This will be the formula for that object. Okay? Small r is radius. You're absolutely right. So small m. Sorry. Americans mess up a lot of stuff. Sorry. My apologies. You're right, usually. But so, well, as you're going to find out, we can substitute d in for it too. You know, d what means diameter, right? It also means lever arm. It also means if you're talking about something like this, where radius is the lever arm. Yeah, too much mean. So I need a volunteer who is not afraid of the dark. First hand wins. Here. Okay? Come here. You can't be afraid of the dark. Okay? Find for yourself down over there. Now, if you're afraid of the dark, you freak out. Sorry. Tell me what you got to say.
Oh my goodness, he's freaking out.
Yeah, alright. So here we have an object with, oh, I was supposed to show you guys that. Okay? Different masses. Okay? There's 3 glue sticks here, right? And 3 glue sticks here. If I turn it about a fixed point, okay, am I really turning these very much? No, theoretically, no. Okay, but you know, theory and reality is a little different. So now if I turn this, what am I turning? Those. Okay, all these weights on here, okay, shouldn't be turned, even though, yeah, I know they're out from the actual axis. If this axis was a straight line and it was right there, a point, if you will, then we couldn't worry about it. But yeah, worry about it. So stand up. Now, are you ready or left? Right. All right. I want you to grab this. I don't know which one you're going to do first. That's right. All right. Put both hands up. Okay. Hold it there and there. Okay. You got it. It's quite heavy, sir. Okay. You got it. You got to step back a little bit. Okay. Now, this is touching your shoulder. Don't let it touch your shoulder. It's all right. Table. Sorry. All right. So I want you to rotate 1 full circle around. And by rotate that. Okay? So I'm going to rotate 1 full circle. Think about how easy or hard it is. Okay, that's a close circle in history. But that's fine, because you're going to do the same, hands back out. You're going to do the same circle. Okay, you got it? You're going to do the same circle, wait. Okay, go ahead. Think about how easy it is to rotate it. So which one's easier? Which one's easier and which one's harder?
The second one was easier.
Second one was harder. That's what I said. And he was correct. You can take off your blindfold. Okay? Well, the thing is, if you're just looking at it, yeah, it looked like it really went around easy after you got started, right?
Right.
An object in motion stays in motion. Okay? Especially when there's a lot of mass here, it's going to stay in motion because of its inertia. Even though it has rotational inertia, it's going to stay there. Okay? But which one was harder to move, he said, was actually when it was like this. It's harder to move around this axis because of all that weight that is further out. Okay? It's easier to move around this axis because all the weight's really inside. Okay? So thank you very much. We got that right twice today. I was very impressed because this is kind of generic. So we're going to calculate, go through a couple calculations with this. Sorry for moving your desk. Back. Sorry. All right, this should look familiar because I just made one of these. Yeah. All right. It says, what is the moment of inertia? So that's I equals mr squared, which is what we're going to use right now. Okay. Of the following point masses arranged in a square. And then we're wondering about the x-axis. If something is rotating about the x-axis, just in case you don't have visual memory, here 2 pointing up, 3 pointing sideways, right? Okay, that's why I did it. This is the x-axis. If it's rotating about the x-axis, it's going this way. So these points on the end, we're not worried about. Okay? Because theoretically, if these are point masses, then they are actually inside of the rod turning. Okay? So we're really not worried about that. We're only worried about these masses out here. So with that said, if we use our equation, I lost my good marker. Can you believe it?
Did you?
Oh, I did. No,
I
you
think
did.
the markers are just bad.
Found it.
You just don't know.
Thank you. I know, that's exactly why. I equals mr squared. Okay? Do you know your mass? What mass do you think we would? Why 4?
Because it's 2 kilograms.
Yes. Okay, because the only masses we're curious about are the ones, this is the x on the y. Okay? Those are the only ones. So the mass would be 4 kilograms. And then we multiply that by r squared. What's the radius? How dare you? Okay? That is not true. Because we have...
I just got scared.
0.3.
Don't be scared. 0.6, that does not look like a radius from the middle
So
out.
it'd be 0.3.
0.3? Are you starting random numbers?
No, because half. I'm waiting to say that was like 0.3.
What would you use? Second fellow didn't get this right. Bam! Sine of theta equals opposite over hypotenuse. You know the theta? You guys have to be course season now. I'm sorry. Sorry, I just can't write that way.
So it'd be
Theta?
90 degrees.
Well, if we want to know this right here, you can use this angle 45 degrees. Because if you think about what a square is, it's 90, 90, 90, 90, cut it in half, and that's 45. Isosceles triangle. So to find opposite, to find your radius, use sine theta, which theta is 45. So hypotenuse times sine of theta equals x or y or whatever you want to call it. They're all going to be the same. So 0.6 times sine of 45 will equal 0.42.
That's the radius.
That is the radius of this square. Okay?
You gotta square that though. We're calculating.
Yes. 0.42 squared. And you get your moment of inertia to be? Oh, it's on the board. Let's just use that one. It's actually 0.71 kilograms times meter squared. It says 0.72 up there. They're just a little bit off. They round it differently. Okay? They round it differently than I did. So, this is about the x-axis. Let's do about the y-axis. That means we're taking it and we are turning it around like this. If you saw my hand move. Okay? We're using the same equation. I equals mr squared. What's my mass this time? 6. She wasn't sure. Yeah, okay.
There is no z-axis.
Okay? Oh, there. How dare you? I equals 6 kilograms times the radius. The radius hasn't changed. So 0.42 meters. And that will give me I of, when you multiply that out, you get 1.06 kilograms times meter squared. Okay? I know it says 1.08. That's fine. Throw in your calculator and you'll get what I got. Alright, who said there was no z-axis? Do you exist? Okay? How would you calculate the volume that an individual takes up? So you need 3 components because it would be in a cube form, right?
So it'll be
Volume takes up a cube. You need something in the length, something in the
width.
width.